Hey there! Tonight we're going on a journey not just through space but through an immense stretch of time. We're going to explore a world that existed long before our own, a world ruled by giants. But before we meet them, we need to understand the stage they walked upon and how it came to be. This isn't just a story of creatures but of discovery. It's about how patient observation, a bit of luck, and a lot of curiosity helped us piece together a narrative spanning hundreds of millions of years. It's a quiet unraveling of Earth's deep past. So, settle in, get comfortable. If you enjoy this kind of journey, consider tapping that like button and subscribing to join us for future explorations. It helps us continue these quiet adventures into the unknown. Our story truly begins not with a roar, but with a whisper from the very rocks beneath our feet. For centuries, people believed Earth was relatively young. But then, a quiet revolution began, led by thinkers who dared to look closer. They observed layers of rock like pages in an enormous, ancient book. Each layer, they realized, represented a different chapter in Earth's history, laid down over unimaginable spans of time. This was the birth of deep time. This idea was profound. It meant our planet wasn't static but dynamic, constantly changing. Mountains rose and fell, oceans appeared and vanished, and continents drifted across the globe like slow-motion rafts. One of the most astonishing realizations was the concept of Pangaea, a single, massive supercontinent that existed hundreds of millions of years ago. Imagine a world where all the land was connected, surrounded by one vast ocean. Evidence for Pangaea came from matching fossil patterns and geological features on widely separated continents. It was like finding pieces of a jigsaw puzzle scattered across the globe, then slowly fitting them together. Now, let's travel back about 252 million years ago to the end of the Permian period. The world was different but vibrant. Life, in its many forms, thrived across Pangaea, from ancient amphibians to early reptiles. Then, something catastrophic happened. Scientists began noticing a stark boundary in the fossil record, a sudden, dramatic drop in the diversity of life. It was as if a switch had been flipped, plunging the world into darkness. This event, known as the Permian-Triassic extinction or the Great Dying, was the most severe mass extinction in Earth's history. It was a moment of profound loss, a planetary reset on an unimaginable scale. Over 90% of all marine species vanished. On land, nearly three-quarters of all vertebrate species disappeared. The world, once teeming with life, became eerily silent, a vast, empty canvas. What caused this devastation? Research points to massive volcanic eruptions in what is now Siberia. For 1,000,000 years, vast quantities of lava poured out, releasing colossal amounts of greenhouse gases into the atmosphere. This led to extreme global warming, acid rain, and ocean acidification. The oceans became deoxygenated, creating vast dead zones where nothing could survive. It was a complex cascade of environmental collapse. The scale of the Permian-Triassic extinction is almost impossible to grasp. It wasn't just individual species disappearing, entire ecosystems collapsed. The world was left scarred, a testament to nature's immense, destructive power. In the immediate aftermath, the early Triassic period was a grim time. The planet was a largely empty place, a world stripped bare. It took millions of years for life to truly begin its slow, arduous recovery. Yet within this desolation lay an extraordinary opportunity. With so many ecological niches emptied, the stage was set for new forms of life to emerge, to diversify, and to eventually dominate. Early paleontologists sifting through Triassic rock layers found sparse but intriguing fossils. These weren't the giants we think of, but small, unassuming creatures, the resilient survivors of the Great Dying. They began to notice that the reptiles emerging in this post-extinction world were subtly different from those that came before. They were often smaller, more agile, and possessed unique adaptations for survival. These discoveries hinted at a remarkable succession of life forms. It wasn't just a random collection of creatures, but a lineage, evolving and adapting over deep time, each group giving way to the next. Among these early survivors, a particular group of reptiles began to show promising signs of diversification, the archosaurs. They were the ancestors of crocodiles, birds, and, crucially, the dinosaurs. Each newly unearthed bone, each fossilized footprint, was a tiny piece of a grander puzzle. Scientists meticulously cataloged them, comparing their structures, trying to understand their relationships. It was through this painstaking work that the faint outlines of the dinosaur lineage began to emerge. They weren't born into a thriving world, but into one recovering from near-total collapse. These early ancestors were not yet the colossal creatures of legend. They were small, agile, and humble, quietly navigating a scarred world, learning to survive and slowly, patiently evolving. The stage was set. From the ashes of the great dying, a new era was dawning. A world once empty was slowly being repopulated, preparing for the quiet emergence of creatures that would one day redefine dominance on Earth. And that is where our journey will continue. The Permian-Triassic extinction had left the world profoundly altered. Yet, even in desolation, life finds a way. The early Triassic period, roughly 250 million years ago, was a time of slow, quiet recovery, a vast, empty canvas awaiting new strokes of evolution. For paleontologists, this period presents a unique challenge. The fossil record is sparse, fragmented. Each bone, each tooth is a precious whisper from a time when life was still finding its footing, rebuilding from near-total collapse. Researchers meticulously catalog these early finds, comparing subtle differences in bone structure, dental patterns, and skeletal arrangements. It is a painstaking process of identifying lineages, tracing evolutionary paths that stretch back millions of years. Among the survivors of the Great Dying, a group of reptiles known as archosaurs began to diversify. These were not yet the colossal creatures we imagine, but modest, agile forms, quietly exploring new ecological niches. Scientists, through careful comparative anatomy, identified key features distinguishing these archosaurs. They were the ancestors of both crocodilians and birds, and within this diverse group, the first faint outlines of dinosaurs began to emerge. Around 230 million years ago, in what is now Argentina, a remarkable discovery was made. The Esquigualasto Formation, a vast stretch of ancient floodplain, yielded an extraordinary window into this nascent world. Expeditions to Esquigualasto are slow, methodical affairs. Teams spread across the rugged terrain, scanning for telltale signs, a peculiar rock texture, a slight discoloration, anything that might hint at bone hidden beneath the surface. It was here, amidst the ancient riverbeds, that paleontologists unearthed the earliest known true dinosaurs, creatures like Aeoraptor and Herosaurus. These were not the giants of later epochs, but modest animals, no larger than a small dog. Their appearance was unassuming, almost shy. They moved on two legs, a crucial adaptation, but their role in the ecosystem was far from dominant. They were small predators or omnivores, living in the shadow of larger, more imposing reptiles. For much of the mid-Triassic, the world belonged to the Crurotarsans, ancient relatives of modern crocodiles. These formidable creatures were the apex predators, the true rulers of their time, far outnumbering and outsizing the early dinosaurs. Scientists studying the fossil record of this period are struck by the humble position of early dinosaurs. They were simply another group among many, struggling for resources, navigating a world still recovering from mass extinction. Yet these early dinosaurs possessed a subtle but significant anatomical advantage: their upright gait. Unlike the sprawling posture of most other reptiles, their legs were positioned directly beneath their bodies, like pillars. This upright posture allowed for more efficient respiration and sustained movement. It meant they could breathe more easily while running, a distinct advantage in both hunting and escaping larger predators. Fossilized footprints provide crucial evidence. The distinct trackways of early dinosaurs show a narrow gait, indicating limbs tucked under the body, a stark contrast to the wider, sprawling trails of their contemporaries. The rocks of Ischigualasto tell a story of quiet persistence. Amidst the dominant Cretaceous, these small, agile creatures were honing their unique adaptations, preparing for a future they could not have foreseen. Each newly prepared fossil from this period offers another piece of the puzzle. The tiny bones, once fragments of ancient life, now speak volumes about the incremental changes that shape evolution. Modern imaging techniques allow scientists to peer inside these ancient bones, revealing intricate details of muscle attachments and joint structures that confirm their unique locomotion. The scientific community's understanding of dinosaur origins has been built on these patient discoveries. It wasn't a sudden explosion, but a gradual, quiet emergence from within a recovering ecosystem. Studies of bone histology, the microscopic structure of fossilized bone, reveal growth patterns. Early dinosaurs grew relatively quickly, suggesting a metabolism that would support their active lifestyle. The teeth of these early forms show varied diets, from carnivorous to omnivorous, indicating their adaptability and willingness to exploit diverse food sources in a world still finding its balance. The quiet Triassic dawn saw the first delicate steps of a lineage that would one day redefine dominance. They were not yet the titans, but seeds of a future empire, patiently waiting for their moment. Their small size and humble beginnings mask the immense potential within their unique anatomy. The upright gait, the efficient breathing, the adaptable diet, these were the quiet innovations. It's a testament to the power of subtle evolutionary advantages. In a world of slow recovery, these small differences would eventually prove to be decisive, though the path was long and winding. The story of their rise is not one of sudden conquest, but of gradual adaptation and diversification, a slow burn over millions of years, largely unnoticed by the dominant life forms around them. As the Triassic period continued, environmental changes would begin to favor these unassuming pioneers. Their subtle advantages would slowly turn into defining strengths, setting the stage for a dramatic shift in Earth's dominant life forms. And that is a story for another time. As the Triassic period deepened, the world continued its slow, inexorable changes. The supercontinent Pangaea, immense and unbroken, began to experience increasing aridity across its vast interior. This shift in climate created new environmental pressures and opportunities for life. Scientists reconstruct these ancient climates by meticulously studying fossilized plant remains and the composition of sediment layers. Each tiny fragment of ancient leaf or pollen grain acts as a delicate barometer of a long-vanished world. The data revealed a landscape gradually transforming, with drier conditions favoring certain plant types and, in turn, influencing the evolution of the herbivores that fed upon them. It was a subtle, yet profound, environmental reshaping. Amidst these changing conditions, a significant evolutionary trend emerged among the early dinosaurs. Some lineages began to grow larger, a crucial step in their ascent. This was the dawn of the sauropodomorphs. One of the most well-known early giants was Cretaceous, discovered primarily in Germany. These creatures were moderately large herbivores, reaching lengths of up to 30 feet, a significant increase from their smaller ancestors. Paleontologists carefully reconstruct their skeletons, piece by painstaking piece. These reconstructions reveal their semi-bipedal posture, allowing them to stand tall and reach higher vegetation, exploiting a new, abundant food source. This ability to browse on previously inaccessible leaves gave them a distinct advantage. It was a quiet revolution in feeding strategies, paving the way for the truly colossal long-necked dinosaurs that would follow. At the same time, another lineage of dinosaurs was also diversifying: the theropods, agile predators who would eventually dominate the carnivorous niches. Sleepless, found in remarkable mass burial sites in New Mexico, is a prime example. These mass graves provide invaluable clues about their lives, suggesting they may have lived and hunted in groups. Their lightweight build and sharp teeth speak of swift, efficient hunting. The discovery of these varied forms, from the browsing Platosaurus to the swift Sleepless, showed that dinosaurs were not just surviving, but actively adapting and branching out into different ecological roles across Pangaea. Yet, the late Triassic was not a period of uninterrupted growth. Another significant extinction event loomed, a global upheaval that would once again reshape life on Earth. Scientists pinpoint this event, known as the Triassic-Jurassic extinction, by a distinct boundary layer in the rock record. This layer often contains evidence of rapid environmental change, including shifts in carbon isotopes. Research points to massive volcanic activity in what is now the Central Atlantic Magmatic Province, or CAMP. Over a relatively short period, immense volumes of lava poured out, releasing colossal amounts of greenhouse gases into the atmosphere. This volcanic cataclysm led to rapid global warming, ocean acidification, and widespread anoxia, or lack of oxygen, in the oceans. It was another cascade of environmental collapse, though less severe than the Great Dying. Many groups of reptiles, particularly the large crurotarsans that had dominated the Triassic, suffered immense losses. Their reign as apex predators abruptly ended. Curiously, dinosaurs, which had remained relatively humble players throughout the Triassic, survived this extinction event with remarkably fewer losses. The fossil record shows a dramatic shift in dominant fauna almost overnight. This sudden clearing of the ecological stage was the turning point. With their main competitors gone, dinosaurs were free to expand rapidly into the newly vacant niches. It was not a conquest, but an inheritance. Their unique anatomical advantages, honed over millions of years of quiet competition, now allowed them to truly flourish. The world was suddenly theirs to explore. Beyond their upright gait and efficient respiration, subtle physiological changes were also taking root. Studies of bone microstructure, or histology, in some early dinosaur fossils hint at higher metabolic rates. These findings suggest that some dinosaurs were developing a more active, perhaps even warm-blooded, physiology. This would have provided them with greater endurance and adaptability in a changing world. While evidence is scarce in the Triassic, faint impressions in some early dinosaur fossils also hint at the emergence of early integumentary structures, precursors to feathers, particularly in some theropod lineages. These quiet innovations, efficient locomotion, varied diets, higher metabolisms, and early body coverings, were the seeds of future dominance. They allowed dinosaurs to rapidly diversify and adapt to almost every terrestrial environment. The Triassic-Jurassic extinction was a filter, a crucible that forged the future. It was the moment when the quiet ascent of dinosaurs became an undeniable surge. From their humble beginnings, these resilient creatures had navigated mass extinctions and environmental shifts, slowly, patiently evolving until the stage was finally and irrevocably theirs. As the Triassic gave way to the Jurassic period, the world was poised for a new era of life. The dinosaurs, now truly ascendant, were about to embark on a remarkable journey of diversification and growth, shaping the Earth in ways unimaginable. And that is where our journey will continue. As the Triassic gave way to the Jurassic period, the world was indeed transformed. The great supercontinent Pangaea, though still largely intact, was beginning its slow fragmentation, leading to shifts in global climate. Lush, humid conditions began to dominate, creating vast, verdant landscapes. Scientists meticulously study fossilized plant remains from this era, revealing an explosion of new flora. Towering conifers, cycads, and ferns created dense, productive ecosystems, providing an abundant food source for the burgeoning herbivore populations. It was within these rich environments that the dinosaurs, now free from their Triassic competitors, began to truly flourish. Their existing adaptations, honed over millions of years, suddenly propelled them into a period of remarkable diversification and growth. The most striking development was the appearance of the sauropods. From their smaller Triassic ancestors, these long-necked, long-tailed herbivores began an evolutionary journey towards immense size, unlike anything Earth had seen before. Early fossil discoveries, often from fragmented remains, hinted at their colossal scale. A single bone, a vertebra, or a limb bone could weigh hundreds of pounds, immediately signaling a creature of unprecedented dimensions. The late 19th and early 20th centuries saw the dinosaur rush, a period of intense, often competitive, fossil hunting. Teams of paleontologists ventured into remote areas, driven by the desire to unearth these magnificent giants. This era of discovery was characterized by immense logistical challenges. Transporting these massive, fragile bones from remote quarries to distant museums required ingenuity, perseverance, and often sheer brute force. Once in the lab, the painstaking work of preparation began. Technicians meticulously cleaned, repaired, and reassembled thousands of bone fragments, a process that could take years for a single complete skeleton. One of the most significant sites for Jurassic dinosaur discoveries is the Morrison Formation, a vast geological unit stretching across the western United States. It represents an ancient floodplain rich with the remains of a vibrant ecosystem. Researchers exploring the Morrison Formation found an unparalleled window into the mid to late Jurassic. The sheer abundance and diversity of fossils here allowed for a much clearer picture of this age of giants. Bone beds, areas where many individuals died and were preserved together, offered tantalizing clues about sauropod behavior. Were they migratory? Did they live in herds? Each arrangement of bones sparked new questions. The reconstructed skeletons themselves became monuments to deep time. Diplodocus, with its incredibly long neck and tail, became one of the most iconic sauropods, representing the pinnacle of terrestrial gigantism. Trackways provided further insights. The enormous, rounded footprints of sauropods, sometimes found in long parallel lines, confirmed their quadrupedal locomotion and suggested group movements. How did they support such immense weight? Studies of their bone structure revealed remarkable adaptations, including hollow, air-filled bones, similar to those of birds, which lightened their skeletons without compromising strength. Microscopic analysis of sauropod bone tissue, known as histology, showed rapid growth rates. This suggested a high metabolism, allowing them to reach their colossal sizes within a relatively short lifespan, perhaps just decades. Brachiosaurus, another Morrison Formation resident, stood out with its long front legs and giraffe-like posture, indicating it was a high browser, reaching vegetation inaccessible to other herbivores. Their teeth, though small for their size, were numerous and constantly replaced, designed for stripping leaves rather than chewing. Their digestive systems likely relied on fermentation to break down vast quantities of plant matter. The Jurassic was not just an age of giants, it was a complex web of life. Alongside the colossal sauropods, other dinosaur lineages continued to diversify, including the formidable predatory theropods. Allosaurus, a powerful bipedal predator, emerged as one of the dominant carnivores of the Jurassic. Its robust skull, serrated teeth, and powerful limbs were perfectly adapted for hunting large prey. Evidence of predator-prey interactions comes from fossilized bite marks on sauropod bones and even shed Allosaurus teeth found alongside herbivore remains. It paints a vivid picture of a dynamic, often violent, ecosystem. The meticulous work of identifying, excavating, and studying these fossils allowed scientists to reconstruct the Jurassic world, piece by painstaking piece, revealing a time when giants truly walked the earth. Each discovery added another layer to our understanding, from the intricate structures of their bones to the vastness of their movements and the complexities of their interactions within the environment. The Jurassic period was, in many ways, the golden age of the sauropods. Their sheer size and numbers reshaped landscapes and ecosystems, profoundly influencing the evolution of all other life forms around them. But the story of dinosaurs was far from over. As the Jurassic drew to a close, subtle shifts in continents and climate would once again begin to reshape the world, setting the stage for even more remarkable adaptations. The Age of Giants was firmly established, but the coming Cretaceous period would see dinosaurs reach new pinnacles of diversity and dominance in ways that continue to surprise and fascinate us. And that is where our journey will continue. As the Jurassic period deepened, the colossal sauropods continued to shape the very landscapes they inhabited. Their sheer mass and numbers meant they weren't just part of the ecosystem, they were ecosystem engineers. Scientists, through careful study of trackways and fossil distribution, began to understand this profound impact. The scale of their feeding habits was immense. Millions of tons of plant matter would have passed through their digestive systems, constantly recycling nutrients. Paleobotanists and geochemists collaborate, analyzing ancient soil samples and fossilized plant remains to quantify this ancient biome's productivity. Understanding their ecological role involved not just their size but their behavior. Did they migrate? Were they solitary or herd animals? Each fossilized bone, each preserved track offered a piece of this complex puzzle, meticulously extracted and interpreted in quiet laboratories. While sauropods dominated the herbivorous niches, other plant eaters were also flourishing, developing new and often surprising defensive strategies. The Middle Jurassic saw an evolutionary arms race begin to escalate, driven by the ever-present threat of large predators. Among the most iconic of these armored dinosaurs was Stegosaurus. Its distinctive plates running along its back and the formidable spiked tail, known as a thagomizer, presented a unique challenge to the era's carnivores. Unearthing these fossils required patience and precision. The function of Stegosaurus's plates has long been a subject of scientific debate. Were they for defense, standing upright to deter attackers, or did they serve a different purpose, perhaps for display or even thermoregulation, helping the animal control its body temperature? Modern scientific techniques such as computer modeling of blood flow patterns within the plates have provided intriguing insights. These models suggest a role in heat exchange, allowing the creature to warm up or cool down efficiently in its environment. However, the thagomizer, the cluster of sharp spikes at the end of its tail, leaves little room for doubt. Fossil evidence, including healed wounds on predatory dinosaur bones, strongly suggests it was a powerful defensive weapon, swung with considerable force. The predators, in turn, continued their own evolutionary journey, becoming increasingly specialized. The theropods, the bipedal carnivorous dinosaurs, diversified into a range of forms, each with unique adaptations for capturing prey in this dynamic Jurassic world. Allosaurus, a dominant predator of the Morrison Formation, exemplified this specialization. Its robust skull, powerful jaws, and recurved, serrated teeth were perfectly suited for dismembering large prey, including the formidable sauropods and armored stegosaurs. Other theropods, like Ceratosaurus, with its distinctive nasal horn and bony crests, suggest different hunting or display behaviors. Each unique skeletal feature offers a clue to its lifestyle, its place in the ancient food web. Scientists piece together these predatory techniques by examining fossilized bite marks on herbivore bones, shed teeth found at kill sites, and even the biomechanics of their skulls. It paints a vivid picture of ancient struggles for survival. Beyond their external forms, a deeper understanding of dinosaur physiology emerged from the microscopic study of their bones, a field known as bone histology. This technique allowed researchers to peer into the very fabric of ancient life. By preparing incredibly thin sections of fossilized bone, scientists could observe growth rings, much like those found in trees. These rings revealed astonishing details about how quickly these massive creatures grew and developed. The data from bone histology showed that many dinosaurs, including the colossal sauropods, grew at surprisingly rapid rates. This suggested a metabolism far more active than previously imagined, challenging the long-held view of dinosaurs as sluggish, cold-blooded reptiles. These findings fueled intense scientific debate about dinosaur physiology. Did their rapid growth imply warm-bloodedness or some intermediate form of metabolism? The answers were nuanced, complex, and varied across different dinosaur groups. Rapid growth also had implications for their life cycles and parental care. If they grew so quickly, how long did they live? How much energy did parents invest in their young? Fossilized nests and juvenile bone beds provided further clues. The study of bone architecture also revealed how their skeletons supported immense weight and withstood the stresses of an active life. Air sacs within bones, similar to those in birds, helped lighten the load while maintaining structural integrity. And quietly, almost imperceptibly, evidence of another remarkable adaptation began to emerge from Jurassic rocks, the presence of early feathers. While more common in later periods, faint impressions hinted at their ancient origins among some theropod lineages. These early feathers were likely not for flight, but for insulation, display, or even camouflage. Their discovery underscored the deep evolutionary connection between dinosaurs and modern birds, a testament to shared ancestry. The Middle Jurassic was a time of dynamic evolution, where the ecological roles of giants were firmly established, and new defensive and predatory strategies were perfected. It was a peak of complex interactions, a vibrant tapestry of life. Each bone, each trackway, each microscopic slice of fossilized tissue added to a more complete picture of this ancient world. The patient work of paleontologists and geologists slowly illuminated the incredible diversity and adaptations of Jurassic dinosaurs. This period of flourishing set the stage for the next great chapter in dinosaur history. The adaptations honed in the Jurassic, from immense size to specialized defenses and efficient metabolisms, would prove crucial for what was to come. As the Jurassic drew to a close, subtle shifts in the planet's geology and climate would once again begin to transform the world. Continents continued their slow drift, creating new landmasses and altering ocean currents. The Age of Giants was still vibrant, but the coming Cretaceous period would usher in an era of even greater diversity, new forms of life, and the ultimate zenith of dinosaur dominance before their final, dramatic curtain call. And that is where our journey will continue. As the Jurassic period receded, the slow, inexorable drift of continents accelerated. Pangaea, once a single landmass, now fractured into distinct continents. This geological reshaping created new oceans and coastlines, profoundly influencing global climates and the distribution of life. Scientists meticulously study ancient sediment layers and geological fault lines, tracing the paths of these drifting landmasses. Each shift in the Earth's crust opened new evolutionary pathways, leading to unique regional faunas across the globe. This continental separation meant that dinosaur populations, once interconnected, began to evolve in isolation. New species arose, distinct from their distant relatives, creating a mosaic of life across the nascent continents. Simultaneously, a quiet revolution was unfolding in the plant world. Flowering plants, or angiosperms, which had emerged in the early Cretaceous, began their rapid diversification. Their vibrant blooms and efficient seed dispersal transformed ecosystems. This proliferation of angiosperms created entirely new food sources and habitats. Insects co-evolved with these plants, leading to a surge in biodiversity that rippled through the entire food web, profoundly impacting herbivorous dinosaurs. Paleobotanists analyze fossilized pollen and leaf impressions, piecing together the ancient flora. The sheer abundance of angiosperm fossils from the mid-Cretaceous tells a story of ecological dominance, reshaping landscapes worldwide. The availability of these new, often softer, plant foods spurred the evolution of specialized herbivore groups. Dinosaurs adapted their teeth and jaws to efficiently process this novel vegetation, a quiet but significant shift in their feeding strategies. Among the most successful of these new herbivores were the hadrosaurs, the duck-billed dinosaurs. Their numbers swelled and they became incredibly widespread, dominating many terrestrial ecosystems. Their most remarkable adaptation was the dental battery, hundreds of tightly packed teeth, constantly replaced, forming a continuous grinding surface. This allowed them to masticate tough plant material with unprecedented efficiency. Scientists reconstruct hadrosaur jaw mechanics through biomechanical modeling, revealing the complex movements that enabled their powerful chewing. This sophisticated feeding apparatus allowed them to thrive on diverse plant diets. Mass fossil discoveries of hadrosaurs, often in vast bone beds, suggest they lived in immense herds, moving across landscapes in search of food. Their sheer numbers shaped the vegetation and nutrient cycles of their world. Beyond the hadrosaurs, the Cretaceous saw the rise of other iconic armored dinosaurs like the ankylosaurs. These living tanks were heavily protected, evolving formidable defenses against the formidable predators of their time. Their bodies were covered in osteoderms, bony plates embedded in their skin, forming a nearly impenetrable armor. Many also possessed a massive bony club at the end of their tail, a powerful weapon for defense. The continental separation also led to the diversification of horned dinosaurs, the ceratopsians. Triceratops, with its massive frill and 3 formidable horns, became one of the most recognizable herbivores of the late Cretaceous. The function of their elaborate frills has long been debated: defense, display, or perhaps a combination. Fossil evidence of combat, including horn marks on other Triceratops skulls, suggests they were used in intraspecific rivalry. And presiding over this transformed world was the ultimate apex predator, Tyrannosaurus rex. Its immense size, powerful legs, and massive skull equipped with bone-crushing teeth made it a terrifying force of nature. Studies of its bite force, estimated to be among the strongest of any terrestrial animal, confirm its ability to crush bone. Fossilized bite marks on the bones of its prey, including Triceratops, offer grim evidence of its hunting prowess. The discovery of complete Tyrannosaurus skeletons, often in association with its prey, allowed scientists to reconstruct its life and behavior. Every bone, every tooth spoke of immense power and adaptation. Trackways of large theropods and their herbivorous prey, sometimes found crossing each other, offer tantalizing glimpses into the dynamic interactions of the Cretaceous. It was a world of constant motion and struggle. Bone histology continued to reveal the rapid growth rates of these Cretaceous giants, suggesting active metabolisms. This allowed them to reach their colossal sizes quickly, dominating their environments for decades. The Cretaceous period represented the zenith of dinosaur diversity and dominance. From pole to pole, in forests, swamps, and open plains, these magnificent creatures flourished in an astonishing array of forms and sizes. The sheer volume of fossils from this period, meticulously collected and studied, paints a vivid picture of a world utterly transformed. Dinosaurs were not just present, they were the architects of their ecosystems. They had adapted to every niche, from the smallest bird-like forms to the largest terrestrial animals ever to walk the earth. Their reign was long, successful, and seemingly unchallengeable. This was a period of unparalleled biological success, a testament to millions of years of evolution, adaptation, and diversification. The world was truly theirs, a vibrant, thriving testament to their resilience. But even as dinosaurs reached the pinnacle of their reign, an ancient world was slowly, imperceptibly, setting the stage for a dramatic, unforeseen change. The seeds of their eventual end were quietly being sown, preparing for a final, profound shift in Earth's history, and that is where our journey will continue. The Cretaceous zenith, a period of unparalleled dinosaur dominance, had been vividly reconstructed from bones and teeth. Yet, a deeper mystery lingered. How did these magnificent creatures truly live? Beyond their skeletal forms, what were their daily routines, their social interactions, their true colors? Behavior, unlike bones, rarely fossilizes directly. Scientists had to become detectives of the ancient world, meticulously piecing together clues from indirect evidence. It was a challenge that demanded patience and a keen eye for the subtle whispers of the past. One of the most revealing forms of evidence came from Trackways' fossilized footprints. These ancient impressions, preserved in mud and sand, captured fleeting moments of movement, offering tantalizing glimpses into the lives of individual dinosaurs and groups. Vast stretches of trackways, particularly from colossal sauropods and herds of hadrosaurs, showed multiple sets of parallel prints. This strongly suggested gregarious behavior, indicating that many dinosaurs lived and moved in herds, much like modern large mammals. Beyond trackways, direct evidence of social and parental behavior emerged from remarkable fossil sites. The discovery of communal nesting grounds, especially those of Maiasaura, the good mother lizard, revolutionized our understanding. At these sites, nests were found clustered together, sometimes with multiple layers of eggs and even remains of hatchlings and juveniles. This suggested that parents returned to the same nesting areas year after year, forming large, protective colonies. The presence of juvenile Maiasaura, too large to be newly hatched but too small to be independent, indicated that young stayed in the nest for an extended period. This implied active parental care, with adults bringing food to the young until they were large enough to forage on their own. Fossilized eggs themselves provided a wealth of information. Scientists could study their shell structure, contents, and even, in rare cases, embryonic remains. These delicate finds offered insights into reproductive strategies and developmental stages. Evidence for hunting strategies and predator-prey interactions often came from more dramatic finds. The famous fighting Dinosaurs fossil, capturing a velociraptor and protoceratops locked in mortal combat, offered an unparalleled snapshot of ancient struggle. This unique fossil showed how these animals might have fought, with the velociraptor's claw embedded in its prey and the protoceratops's beak clamped onto its attacker. It was a frozen moment of prehistoric violence, preserved for millions of years. Beyond such rare direct encounters, bite marks on fossilized bones provided widespread evidence of predation and scavenging. The size, shape, and spacing of these marks could often be matched to specific dinosaur teeth, identifying the ancient aggressor. Understanding dinosaur diets also relied on meticulous analysis of their teeth. The shape, number, and wear patterns on teeth offered crucial clues. Flat, broad teeth indicated plant eaters, while sharp, serrated teeth belonged to carnivores. Perhaps the most direct evidence of diet came from coprolites' fossilized dung. Though often overlooked, these ancient droppings were time capsules, preserving undigested fragments of meals from millions of years ago. Within coprolites, scientists found everything from plant fibers and wood fragments to bone shards and fish scales. This allowed for precise reconstruction of what different dinosaur species consumed, revealing complex food webs. The combination of tooth morphology, bite marks, and coprolite analysis painted a detailed picture of diverse dietary strategies. Some dinosaurs were strict herbivores, others dedicated carnivores, and a few were omnivores, adapting to their specific environments. Beyond behavior and diet, a more elusive question persisted. What did dinosaurs truly look like? For decades, their appearance was largely speculative, based on skeletal reconstructions and comparisons to modern reptiles. But then, new discoveries offered a glimpse beneath the bone. Fossilized skin impressions, though rare, provided direct evidence of their integument. These impressions revealed textures, patterns of scales, and sometimes even folds of skin, hinting at the contours of their bodies. The true breakthrough came with the discovery of melanosomes in exceptionally preserved fossilized feathers and even skin. These microscopic pigment-carrying organelles, though tiny, held the key to unlocking the colors of dinosaurs. The shape and density of these fossilized melanosomes correspond to specific colors in living animals. Spherical melanosomes often indicate reddish-brown hues, rod-shaped ones suggest black or gray, and highly organized ones can even imply iridescence. This incredible scientific advancement allowed researchers to reconstruct the actual colors and patterns of some dinosaurs. The world of drab, gray giants began to transform into one of vibrant, often striking hues. The discovery of dinosaur coloration opened new avenues for understanding their behavior. Colors could have served for camouflage, blending into their environment, or for display, attracting mates or intimidating rivals, much like in modern birds. The implications were profound, especially for feathered dinosaurs, further solidifying the deep evolutionary link between dinosaurs and birds. Their ancient plumage, once thought to be purely speculative, now revealed a spectrum of colors. These revelations transformed our perception of dinosaurs from sluggish, lumbering giants to dynamic, intelligent, and often colorful animals. Their lives were complex, filled with social interactions, parental care, and intricate ecological roles. The patient, interdisciplinary work of paleontologists, geologists, and molecular biologists slowly but surely peeled back the layers of time, revealing a living, breathing prehistoric world in all its vibrant complexity. Yet, even as humanity gained an unprecedented understanding of their lives, the story of the dinosaurs was destined for an abrupt and dramatic end. Their long reign, a testament to millions of years of adaptation, would soon face an ultimate, unforeseen challenge. And that is where our journey will continue. The Cretaceous period, a time of unparalleled dinosaur dominance, seemed to stretch endlessly. Yet, as the final millions of years unfolded, observant scientists decades later would begin to notice subtle, almost imperceptible shifts in the fossil record. Not a sudden collapse, but a quiet, complex change. Paleontologists sifting through strata from the late Cretaceous found that while many dinosaur groups still thrived, some seemed to be experiencing a slow decline in diversity. This was not a clear signal, and the evidence often sparked intense debate among researchers. Distinguishing natural fluctuations from true signs of crisis was a profound challenge. Earth's history is filled with waxing and waning species. The task was to find a pattern, a trend that hinted at something more significant than everyday evolution. Meanwhile, marine biologists studying ancient ocean sediments noticed clearer signs of stress. Microscopic marine organisms vital to the ocean's food web showed a more pronounced decline in the fossil record, suggesting environmental pressures were building. Beyond the biological shifts, geologists began to uncover evidence of immense, long-term environmental stresses. In what is now India, vast flood basalts known as the Deccan Traps revealed a story of monumental volcanic activity. For hundreds of thousands of years, colossal volumes of lava had poured across the landscape, creating layers of rock miles thick. This was not a single eruption, but a prolonged period of intense geological upheaval, releasing immense quantities of gases. The sheer scale of these eruptions would have injected vast amounts of carbon dioxide and sulfur dioxide into the atmosphere. This would have led to drastic climate swings, from warming to cooling, and widespread acid rain, profoundly altering global ecosystems. Further evidence of environmental instability came from fluctuating sea levels. Sedimentary layers around the world showed repeated advances and retreats of ancient oceans, disrupting coastlines and marine habitats, a slow, relentless pressure on life. Global climate models built from diverse geological data pointed to a general warming trend through much of the late Cretaceous, punctuated by periods of rapid cooling. Such instability would have challenged even the most adaptable species. These long-term environmental stressors, the volcanism, sea level changes, and climate shifts, led many scientists to hypothesize a gradual cumulative decline for dinosaurs, a slow erosion of their dominance. But then, a sharp, unexpected clue emerged. Geologists seeking a precise boundary between the Cretaceous and the subsequent Paleogene period looked for a clear marker in the rock record. They sought a distinct layer of sediment that would represent the very end of the dinosaur age. In the late 1970s, Walter Alvarez, a geologist, was studying limestone layers in Gubbio, Italy. He observed a thin, distinct layer of clay, only a centimeter thick, separating Cretaceous rocks from Paleogene ones. It was a clear, sudden break. To determine how long the clay layer represented, Walter's father, Luis Alvarez, a Nobel laureate physicist, suggested analyzing its iridium content. Iridium is rare in Earth's crust but abundant in meteorites. The results were astonishing. The clay layer contained an iridium concentration hundreds of times higher than typical crustal rock. This anomaly, this spike in a rare element, pointed to a source beyond Earth's normal geological processes. Luis Alvarez and his team proposed a radical idea. The iridium spike was the signature of a massive asteroid or comet impact. Such an event, they theorized, would have caused a global catastrophe, plunging Earth into darkness and leading to mass extinctions. The impact theory was met with significant skepticism. It challenged the prevailing scientific view of gradual change, a cornerstone of geology. The idea of an extraterrestrial event ending the age of dinosaurs seemed too dramatic, too sudden. This resistance reflected a long-standing debate in geology: uniformitarianism versus catastrophism. Uniformitarianism, the idea that geological processes operate slowly over vast timescales, had largely prevailed since the 19th century. Despite the initial skepticism, the iridium anomaly prompted other research teams to search for similar layers elsewhere. If it was a global event, the iridium signature should be found worldwide at the Cretaceous-Paleogene boundary. Indeed, the iridium layer was found in dozens of sites across the globe in marine and terrestrial sediments, confirming its global nature. This widespread evidence began to shift the scientific consensus. Further corroborating evidence emerged. Shocked quartz, mineral grains deformed by immense pressure found only at impact sites, and tektites, small glass spherules formed from molten rock ejected during an impact, also found globally at the boundary. With the global evidence mounting, the next crucial step was to find the impact site itself. A crater of such immense size would be difficult to hide, but it might be buried, eroded, or submerged beneath the ocean. Through decades of geophysical surveys and drilling, a massive, buried circular structure over 180 kilometers wide was identified beneath the Yucatan Peninsula in Mexico, the Chicxulub crater. Its age perfectly matched the KPG boundary. The discovery of the Chicxulub crater, combined with the iridium anomaly and other impact evidence, provided overwhelming support for the asteroid impact theory. It was a triumph of interdisciplinary science, piecing together a cosmic puzzle. Today, the scientific consensus is that a colossal impact event delivered the final, devastating blow. However, many researchers also acknowledge that the long-term environmental stresses like the Deccan Traps volcanism may have weakened ecosystems, making them more vulnerable to such a catastrophic shock. The shadow had lengthened, the signs of change had been read, and the scientific community had pieced together the incredible story of a world poised on the brink. The stage was now set for the immediate, dramatic aftermath of that fateful day, when the long reign of the dinosaurs would abruptly end. And that is where our journey will continue. The long reign of the dinosaurs, which had stretched for 165 million years, was drawing to an abrupt close. The signs, once subtle, now converged on a single cataclysmic event, preserved in a thin layer of clay around the globe. It was the ultimate, unforeseen challenge. 66 million years ago, a massive asteroid, estimated to be 10 to 15 kilometers wide, hurtled through space. Its trajectory was set on a collision course with Earth, specifically the shallow seas off the coast of what is now the Yucatan Peninsula. The asteroid entered the atmosphere at an unimaginable speed, perhaps 20 times faster than a rifle bullet. It created an incandescent fireball, briefly outshining the sun, visible across continents. The impact itself was an event of staggering energy, equivalent to billions of atomic bombs. It vaporized instantly, creating a crater over 180 kilometers wide and 20 kilometers deep. The ground beneath buckled and rebounded violently. The immediate shockwaves propagated globally, triggering massive earthquakes and volcanic activity far from the impact site. Colossal tsunamis, hundreds of meters high, swept across ancient coastlines, inundating vast stretches of land. Incandescent debris ejected into the upper atmosphere rained back down across the planet. This thermal pulse ignited widespread wildfires, consuming forests and releasing immense quantities of soot into the sky. The impact also blasted billions of tons of pulverized rock and dust high into the stratosphere. This fine particulate matter, along with the soot from wildfires, formed a global dust cloud, encircling the Earth. For months, perhaps years, this impenetrable cloud blocked out the sun's light. The world plunged into an impact winter, a period of prolonged darkness and dramatically plummeting temperatures. Photosynthesis, the very foundation of most ecosystems, ground to a halt. Plants withered and died, triggering a catastrophic collapse of food webs across both land and sea. The immense energy of the impact also superheated the atmosphere, causing nitrogen and oxygen to combine, forming nitric acid. This led to widespread, devastating acid rain, further poisoning ecosystems. The consequences were dire and widespread. Large herbivores dependent on abundant vegetation starved. Carnivores, in turn, lost their prey. The intricate balance of life was shattered. Non-avian dinosaurs, those magnificent creatures that had dominated for so long, were particularly vulnerable. Their large size and specific dietary needs made them unable to cope with the sudden, drastic environmental shifts. Yet the extinction was selective. While around 75% of Earth's species perished, some groups survived. Scientists meticulously study the characteristics of the survivors to understand why. Many mammals, generally small and often burrowing, were able to shelter from the initial heat and subsequent cold. Their diverse diets, including seeds and detritus, allowed them to persist through the long darkness. Crucially, some avian dinosaurs, what we now call birds, also survived. Their smaller size, ability to fly to find scattered resources, and varied diets likely played a key role in their resilience. In the oceans, the collapse was equally severe. Ammonites, mosasaurs, and plesiosaurs vanished. The oceans became acidic, and the base of the marine food web disintegrated. The KPG boundary layer, with its iridium spike, shocked quartz, and tektites, remains a profound testament to this day. It is a scar on Earth's history, a geological signature of cosmic intervention. After the cataclysm, a profound silence fell over the planet. The roars of tyrannosaurs, the trumpeting of hadrosaurs, the thunder of sauropod footsteps, all were gone. A new, quieter world emerged. Over millions of years, Earth slowly healed. The dust settled, the temperatures stabilized, and life, ever persistent, began its slow, arduous recovery, adapting to the changed conditions. With the ecological niches left vacant by the dinosaurs, mammals began their remarkable diversification. From small, unassuming forms, they would evolve into the dominant large animals of the Cenozoic era. And the legacy of the dinosaurs continues to soar above us. Every bird we see, from the smallest hummingbird to the largest eagle, is a direct descendant of those ancient, feathered theropods. They are living dinosaurs. Our fascination with dinosaurs remains undimmed. They spark our imagination, remind us of Earth's deep history, and challenge us to understand the immense forces that shape life and extinction. Through the patient work of scientists meticulously sifting through rock and bone, we have pieced together this incredible narrative. Each fossil is a whisper from the past, a clue to a story spanning eons. The rise and fall of dinosaurs reminds us of the delicate balance of life on Earth and the profound, sometimes sudden, changes that can reshape our world. It is a story of wonder, resilience, and the enduring mystery of deep time. And so, as the moon climbs high and the echoes of ancient giants fade into the quiet of the night, we reflect on their incredible journey. Their story is complete, yet their legacy continues to inspire our curiosity. Sleep well.